Math 1314, Tyler Junior College, Section 3.4, Zeros of Polynomial Functions. This first video follows immediately from the end of the last video in the previous series for Section 3.3, Polynomial Division, Remainder, and Factor Theorems. So allow me to summarize. At the end of the previous video, we were looking for the zeros of the function f of x equals 2x to the third power minus 3x to the second power minus 11x plus 6. So we set that equal to 0. We were also told in that problem that x equals 3 is a zero of the function, meaning x equals 3 is a root of this equation. If we substitute 3, it makes it equal to 0. The factor theorem said that if x equals 3 is a 0, then x minus 3 is one factor of the function. So we use synthetic division by dividing the function by that factor to get the other factor of 2x squared plus 3x minus 2. So quite a bit happened between the first and the second steps. But once we got there, we were down to a quadratic factor, highest power is x squared. And although we could set that equal to 0 and solve it using the quadratic formula, I chose to go ahead and factor it so that we could have the following discussion. The final three factors were x minus 3, 2x minus 1, and x plus 2. And upon setting each factor equal to 0, we got zeros of x equals 3, x equals 1 half, and x equals negative 2. Remember, when I say a zero of a function, I mean a value that makes the function equal to 0. If we substitute 3, we get 0. If we substitute 1 half, we get 0. If we substitute negative 2, we get 0. But the biggest problem about solving this equation, or equivalently finding the zeros of this function, was we were given a hint at the beginning as to what one of the zeros was. It wasn't a hint, we were flat out told x equals 3 is a 0. Well, that set off a chain of events. Okay, so x minus 3 is a factor. Let's do a division problem to get the other factor, and now we can move forward. But what if we weren't given that hint? What if we weren't told, by the way, x equals 3 is one of your solutions, one of your zeros of your function, and we were just told, here's your function, find its zeros, with no hints? Well, the truth of the matter is, even when you're given no hints, there are still hints. You just have to know where to look. So the question we're going to attempt to answer is, where are these zeros embedded in the original function? In other words, where in the original function were hints that we could have gotten 3, we could have gotten 1 half, we could have gotten negative 2? To answer that question, we're going to reverse engineer the problem. We're going to start at the end and work our way back up to the beginning. But as we're moving upwards, we're going to keep track of where all the zeros go. And not just the zeros, but their numerators and denominators. Because every integer can be written as a rational number, in other words, every number that looks like a whole number can be made a fraction by putting a 1 under it, we're going to treat all of these as fractions just for the time being by putting the 3 over a 1 and by putting the negative 2 over a 1. And now we're going to try to reverse engineer and see where all the numerators and denominators went back in the original function. Let's start with the numerators. I'm going to circle this 3 in blue, and it should be pretty obvious where the 3 is in the line above it. The 3 in the line above it is right here, and it's also here. Okay, that's not too bad. Let's track down the other numerators. This numerator is 1, but where in the factor above it is the 1? It's right here. Now, going up a line, we did a FOIL problem, so before we do that, let's keep track of this numerator. Now, I know it was a negative 2, but let's not worry about the negative just for a moment. This 2 in this fraction came from this 2. And now we have to do a little more scrutinous, if you will. Because going up another line, these two factors got FOILed into this one. And as a FOIL problem, these numbers do a lot of things. They don't show up in the first part of the product, but they show up in the outside part and the inside part. But the outside and the inside get added, and so those numbers get combined after getting multiplied by a 2 over here to make the 3x in the middle. When you add numbers together, there's an infinite number of ways to take them back apart. For example, if I said I added two numbers and got 5, what are the two numbers I could have added? 0 and 5, 1 and 4, 3 and 2. But that's not all. 6 and -1, 7 and -2, 8 and -3, 9 and -4, and so on and so on and so on. So if I'm trying to recover two numbers that got added, good luck with that, because there's an infinite number of ways to add integers to get a given sum. But when restricted to integers, there's only a finite number of ways to recover a product. For example, if I said I multiplied two integers, no fractions, two integers, and got 5. Now I only have two choices. It was either 1 times 5 or -1 times -5. So my point is, when you combine two integers to make a new integer, if you combine by adding, there's an infinite number of ways to create that given sum. So it's impossible to say, well, maybe it was this pair. But when you multiply, there's a limited number of ways to get a product. Even if it was a product as juicy as 24. Well, 24 as an addition problem, there's an infinite number of ways to get it if you allow negatives, still no fractions. But to multiply and get 24, there's 1 times 24, 2 times 12, 4 times 6, 3 times 8. Yeah? And they're negatives. -1 times -24, -2 times 12, -4 times 6, -3 times -8. So even though 4 is a juicy and very composite number, there's only 8 ways to multiply integers to get it. So my point is, if we're going to keep track of where these numbers go as we move upwards, we really want to only focus on when they multiply and not when there's any adding involved. So as a FOIL problem, if we were to FOIL this out, the inside and the outside start out by multiplying, but then they get added to combine the like terms, making it next to impossible to recover the numbers that got added. But the last part of FOIL, these get multiplied, and it's easy to recover numbers when you have a product. So we're going to keep track of this 1 and 2 as in terms of where they go in the FOIL process upon getting multiplied. The 1 times 2 made this 2 here. And using the same argument, if we were to distribute and combine like terms, anywhere where we add makes it impossible to recover the numbers that were added. There's an infinite number of ways the addition could have happened, but only a finite number of ways we could multiply integers to get a certain product. So as we move upward again, we're only going to focus on where these guys get multiplied. And when these guys get multiplied, they make this 6. So there's the answer to part of the question. The numerators of the zeros were embedded in the constant term. But what about the denominators? The denominators of these fractions were 1, 2, and 1. Let's take the middle fraction. This 2, where was it in its factor in front of the x? The leading coefficient, if you will. Now the 1's a little stealthier because we kind of artificially slipped the 1 in there, but there is a 1 in this factor. It's the coefficient of the x. And the same thing over here. So let's keep track of where those go. Going back to the FOIL problem. If we want to keep track of these and try to recover them, we only want to focus on products, not sums. And the only product involving these numbers is the first part of FOIL. 2 times 1 is 2, and that would show up here. Of course, this 1 is still there. And similarly, moving back upwards, in order to recover these two numbers, we can only recover them from a product, not from a sum. So we need to locate where in the original function these two numbers were multiplied, and if they were multiplied, they created the x cubed term. So 1 times 2 gave us the 2 in front of the x cubed. So the answer to the question, where are these zeros embedded in f of x? The numerators were embedded in the constant term, the number at the end, and I should have written that. Oh, I did write it in blue. The numerators of our zeros were embedded in the constant term. The denominators were in the leading coefficient. Now be careful. That doesn't mean, oh, if I'm a factor of the denominator, if I'm a factor of the constant term, then I must be a numerator. For example, 6 is a factor of the constant term, but 6 was not a numerator. Here we did have every factor of the leading coefficient as a denominator. The only factors of 1 and 2 are 1 and 2. So how can we take this observation and transform it into something that we can use to help set off this flow when we're not given a 0? Well, the answer to that is what the next video is about.